Hello, and welcome to this session about InFutUReWood. And I'm really happy to introduce this subject. It's very complicated and complex, but we have tried to solve all the questions. As you can see in this photo, it's Kiruna, a city in the north of Sweden, and they are moving this city. And since they're moving the city, they have to think about these questions. Should they reuse the houses, or should they be demolished? And the Kiruna municipality is a part of the project. We will have 10 minutes in the end for questions. So if you have questions, you can use this menti.com, or you can write the questions in this Vimeo stream chat. InFutUReWood tries to explain or to answer the questions, how should we build today to be able to circulate tomorrow? And to do so. But the question is, why? Why should we do this? Why should we reuse wood? Why should we recycle? Wood is a renewable source. The trees grow and up again, binding carbon dioxide. But we do this because we have to, from many points of view. And you can see some of them here. And this is a priority in EU and in national regulations and in initiatives for sustainable use and natural resources, and for collection, reuse and of materials and waste. On this photo session, to the left you can see a yellow house, and it had been moved in the city of Kiruna to a new location, and this house is 120 years old. But most of the houses, they don't go this way. They have to be moved. They are more demolished, as you can see in the following sections, and they are going to be heat in our different heat. So that's why we have to do this. To be able to reuse them, the quality have to be good enough. And as you can see on the photos, they are not. To solve these problems, we are 22 partners, as you can see to the left. And we also have divided the work into 7 work packages. And today we are present things from work package 2, design of timber structure for the future. Work package 3, product design using recovered timber. Inventory, destruction and quality of recovered wood. We also have presentation from properties of recovered wood and also environmental and economic assessment. So you will hear more about this during the presentations. And we also have a web page, as you can see down there. And we are a few persons here today having this presentation, but we have been many more persons to prepare this presentation and also joining the project. So this is some of the persons that have helped up. And I also give a reminder here if you have any questions during the day or our presentation. And now I give over to Bahar Nasiri.
Thank you, Karin. Good afternoon, everybody. I'm Bahar Nasiri. I'm actually from Aalto University. And today I present part of the work that we've done in InFutUReWood project, and the topic is about inventory deconstruction and quality of recovered wood. The objective of the work we've done was to understand the volume, dimension, and criteria influencing the quality of reclaimed wood, and also to understand why prioritizing reuse and recycling of wood through cascading is important. To understand it as a first step, together with our colleagues in Spain and Ireland and us in Finland, we inventory timber products in residential buildings, and our analysis basically showed that, for example, in Finland, 17.5 megatons of timber is in structural parts of residential houses in 2017, of which 60% are from houses built pre-1969. In Ireland, even though masonry construction has been the dominant construction method, but still wood can be found in large quantities. And as you can see in this figure, 60% of the estimated stock is from B4.5 timber. And also in Spain, it was basically found that pre-modern buildings are a good source to find reclaimed wood. And this is due to the different dimensions that we can get from these buildings, and also their joinery technique is basically metal-free, which is basically favorable for reuse as well. But even though we have all these resources, still reuse and recycling haven't been implemented in practice yet. To understand why, we basically talked to demolition waste management and wood processing companies in our partner countries. And of a few basically insights that we got from from talking to the basically people in industry, and also where possible we also conducted site visit, was that mechanical demolition basically degrades the quality of wood, while deconstruction can decrease the risk of damage to wood. However, at the moment, deconstruction is not economic, time-efficient, and viable alternative for contractors. The design of buildings are not basically, it doesn't basically allow demolition contractors to extract the materials intact, and even when there is an opportunity, and it can be, for example, easily reused or recycled. So it is imperative to basically develop accessible practical guidance on the development of design for deconstruction and reuse. What we also find out was that the quality of reclaimed wood is basically unknown at the moment. The demolition contractors do not record any information about the condition of wood, which is basically difficult to reuse or recycle the material which you don't know about. Also, for example, in the, as you all know, during the use phase and demolition phase, the damage to wood may occur, and also traditionally in some buildings, wood preservatives have been used for example, improving the resistance to decay. And those materials cannot be reused or recycled at the moment because the substances used for basically, the substances are basically hazardous. To basically, to see what we should basically consider, we came up with this criteria, as you can see on this figure, that should be evaluated basically to determine whether the condition of wood meets the requirements for the production of new products or not. We came up with, let's say, a pre-sorting system to understand what we have as a secondary resource at the moment. And in the last, I want to highlight that why basically it can be beneficial to prolong the lifetime of wood through cascading. As you can see in this figure, extending the lifetime of wood will lead to significant variation in future outflow when the lifetime of wood increases. Wood waste has a polynomial correlation over time, and it reaches its peak at later time when its lifetime increases. With that in mind, basically, you can imagine that how long life of materials can benefit resource efficiency and also following that climate change. I want to summarize the basically key findings by saying that the work we've done, basically timber used for construction of residential buildings was inventoried in Finland, Ireland, and Spain. And the existing buildings in these countries contain a large amount of timber that could be reused or recycled. We also investigated the end of life of buildings, and through that, possible improvements and issues hindering wood cascading from existing buildings were identified. We also developed a criteria influencing the visual quality of wood, and also developed a procedure that you can basically evaluate the visual quality of wood. In Finland, we also run a dynamic stock analysis and estimated the future wood waste scenarios for residential houses built after 1966. Thanks for listening. Here is our contact detail also. And with that, I want to give floor to our next presenter, Marlene. Thank you.
Thanks, Baha. So apparently we do have a lot of recovered timber that could potentially be reused, but we do need some methods of assessing the properties of this timber. And we worked on grading approaches for recovered wood, mostly at Edinburgh Napier University, at the Polytechnic University in Madrid, and at the University of Ljubljana. And my colleague Dan Ridley-Ellis has prepared a short video of our main results. It goes quite quickly, so if you're interested in the topic, do rewatch it on our YouTube channel, InFutUReWood. And we also put in some links to other sources where you can learn a bit more in detail about grading of recovered timber. Let's hope this video starts.
Strength grading of structural timber isn't only about strength, but strength is the most difficult part of it. We can only measure strength destructively, so we have to use predictions and a probabilistic approach. This is done with the characteristic value at 5th percentile. We grade in such a way that no more than 5% of the pieces have a strength lower than the strength class requirement. We just don't know which pieces they are unless we break them. With new timber, we make use of information about species and growth area, because both of those affect the link between the things that we measure in grading, the indicating properties, and the things that we are predicting, the grade determining properties. These correlations are more like associations than direct causal relationships. Knowing species and growth area is not really possible for recovered wood, and is also complicated by growth conditions having changed over time, perhaps changing those correlations that we rely on. But anyway, the current grading approach is inadequate because of something else even more important that might have happened. It might be that there was some prior grading or sorting. Perhaps something happened in service that changed the timber properties. If that selectively removed more of the stronger pieces, the characteristic value is reduced below what we think we have. If we know the original grade of the timber, we have some helpful information, but we cannot necessarily rely on that. And anyway, who is responsible for that declaration of performance? We better have a way to grade recovered wood so that we can confidently use it. The visual override step is like it is for new timber and serves the same purpose, but we need to include a few additional things that cover additional problematic defects that occur in recovered wood, such as drilled holes and cut notches. This builds on the sorting criteria developed in Work Package 4. After we've done this, all the timber that we send to the grading process is potentially usable. The new strength grading process can be outlined as follows. Use grading technology to assess each piece and get a probabilistic prediction of the key properties of that piece. Density and stiffness are pretty easy to do. Next, combine that probabilistic prediction over a set of pieces to get a combined probabilistic description of the set. Practically, this can be achieved by treating each actual piece as a multitude of possible pieces, representing all the potential strengths, so that we can work in a non-parametric way with numbers rather than distributions. Think of it as like seeing all the possible future timelines at once. So, for this example here, we have one piece with a certain indicating property value. That gives us an expected value for the strength, and a measure of how much it might vary from this. We can take a set of equally likely possible pieces, which covers the results we would get if we could test that piece many times, as if in slightly different parallel universes. That allows us to calculate characteristic properties of that set of pieces in the same way that we do now for new timber. We compare that to what we need for the target strength class or the application, and if necessary, we remove some of the pieces from the set to raise the characteristic values. When we remove an actual piece, we remove all the associated possible parallel universes pieces in that dataset. In simple terms, comparing to how we grade new timber at the moment, we go from properties predictions made on populations of timber to making properties predictions on a piece-by-piece basis. But we also go from making grading sorting decisions on individual pieces to making grading decisions based on information from sets of pieces. We still need to verify the grading, and this can be done with a combination of destructive testing a portion of the graded timber and monitoring of the grading indicating properties to look for any problematic changes in the correlations. The data from the verification can help build better predictive models, making the grading process less conservative as more timber is graded. To be able to do this, we still need to have some level of homogeneity in the timber being graded. But we don't need to be so specific about knowing species and growth area as we do when we apply the current approach used for strength grading new timber. Crucially, we can also compensate for the possible prior grading or sorting. But that's not everything that we need to consider. There are perhaps degradation processes that affect secondary properties that make it different to new timber, tension strength and increased tendency to split, for example. That's something investigated in Work Package 4, and as far as the grading method goes, more research might mean that we need a different set of secondary properties equations. With wood, what sounds simple in theory isn't always simple in practice, and the only way to properly discover the complicated things is to try it for yourself. So as part of the work package, recovered spruce and oak beams were measured and tested. Results were compared to what we expect to see for new timber, but the main reason for doing this work was to uncover the practical difficulties of actually doing things. Getting the required basic information about recovered wood will require a lot of testing, although some of this can be done as part of a commercial process, a combination of grading data and production testing. Some of this approach can also be applied to timber in situ to assess properties that hopefully keep the timber in service longer through renovation and repair before reuse. In situ timber is more difficult to assess and measure, but we do have the advantage of knowing what each part is doing in the structure. In summary, strength grading as we do it now isn't going to work for recovered wood, but much of the modern technology that we have for grading can be used very effectively for a different approach to strength grading. This new approach can result in strength classes that work in the same way as the ones that we're familiar with, but those strength classes might need to have different properties profiles to take advantage of the good knowledge that we have about stiffness and density, and not be disadvantaged by the need to be a bit more conservative about strength. Since not all timber engineering design is limited by strength, this isn't necessarily a big disadvantage for using recovered wood.
Yeah, so in some way we can assess the properties of recovered wood, and that would give us a basis for making structural products from recovered timber. My colleague Annette Hart from NUI Galway will talk a bit more about that.
Okay. Okay, so thank you very much, Marlene, for the introduction. And so what I'm going to speak about is I'm sorry, the light is very blinding. I must move to one side. I'm going to talk about some work we did as part of Work Package 3, looking at this resource that we've been talking about, this recovered material, and how we can actually extend the service life of that. So I'm going to talk here really about just two elements of the work that we've done, in which what we've done is we've taken some recovered softwood and hardwoods, and we have produced mass timber products. And as a way of assessing the relative performance, what we've done then is looked at trying to get some equivalent products from new timber. So the studies that I'm going to discuss today are studies that were carried out in the National University of Ireland in Galway and also the Polytechnic University in Madrid. And I'd like to acknowledge my colleagues who are not here, Dr. Daniel Lana and Dr. Guillermo Inoguez, who carried out the work in Spain. So for these studies, we sourced some spruce and some oak. And from this material from demolition sites, we produced CLT from the spruce, and we used the oak to produce both CLT and also glued laminated timber. So to start off with the Irish study, in which we are looking at the spruce, the material that we used came from the demolition of a 1980s office building in Dublin. And this was being demolished by our project partners, Hegarty Demolition, who took this material from the roof structure for us. I should say that this building was unoccupied for several years before the demolition took place. And also there had been some water ingress into the roof area through some damage to the roofing itself. So the timber which was taken out had a relatively high moisture content, between 18 and 24%. Looking at the timbers that were taken out, we found some grade stamps on those timbers, and it indicated that it was not, in fact, Irish timber that was used. It was a European spruce, which is graded to what we use in Ireland and the UK for timber trusses. It's a grade TR26. So at least we had some idea of the source of this timber and what its relative properties should be. I suppose from a practical perspective, in terms of using this material for what we have to do to actually reuse this material in a practical sense, one of the issues that occurs here, not only referring to coatings as was referred to earlier, but also in the case of many of our structures, such as trusses, we have a significant amount of metallic material, and removing that without damaging is really quite a problem. And what we discovered, in fact, in this and in a number of the other site surveys that took place, was that it's not only the connectors that the engineers have designed that we're finding here, but the carpenters during erection seem to love to use a lot of other nails to assist them to facilitate the erection. So I suppose these are some of the issues that we need to look at in the future. If we're going to try and practically reuse these materials, how can we avoid some of these issues that we're addressing? So in the first stage, I suppose, of the assessment of this material, we carried out some non-destructive testing of the material that we collected using an MTG handheld acoustic grader, which allowed us to then determine the dynamic modulus of elasticity of the boards. And you'll see here the distribution of properties, and the vast majority of boards there lay in the region between about 11 and 14,000 newtons per square millimetre. And I suppose this presented a bit of a challenge for us, because what we want to do is manufacture products from the recycled material, but also comparable products from new material. But of course, the new spruce in Ireland doesn't have these properties. So what we had to do was we had to move, and we used Douglas fir batch instead, and that's why there are two different species used here. It's really to match this. And we did a similar evaluation of the Douglas fir, and we found that we had a batch with a very similar range of dynamic modulus of elasticity values. So using these two batches of material, then we manufactured small cross-laminated timber panels for testing and bending. We had three 3-layer panels, which were 60 millimeters deep. This is a piece of one of the panels made from the recovered spruce. So we had 3 different designs then for each case. We had the recovered material, we had the new material, but we also decided we would try and look at a hybrid panel, because a lot of the material that we're getting from recovery is short material. And obviously we can join it with finger joints, but we're going to have a lot of finger joints. So perhaps maybe we look at partially replacing new material. So this is the reason for considering the hybrid example here. So these were tested in bending according to the standard, and this is what we found. Essentially here, the failure mode was what we expected from testing cross-laminated timber in bending, that we had failure initiating at the tension face, near the location of a knot or large slope of grain, which propagated then through the section. Looking at the comparative results from the 3 batches that we created initially, the mean value of the modulus of elasticity highlighted in red there, so this is the global modulus of elasticity, we can see that the results are very comparable, which of course we could expect because they have matched dynamic modulus of elasticity. But what it does say is that the bonding has been effective between the layers, so that we're retaining the values. Looking at the strength, we were actually rather surprised to find that the strength values were also the same. Now, there may be various reasons for that. The timber is only 40 years old, so it's relatively young. I mean, we're talking about really extending service life. But it's shown that even with material that has been subject to very adverse conditions in the more recent years of its life, that everything that we're getting good properties from it. We also created another batch of 3 hybrid panels from the remaining material, which had a lower global modulus of elasticity, and we didn't find anything strange about the results, lower properties in general. So just based on this initial study, this seemed to be something that was working quite well. Moving on to the study that was carried out in Spain by our colleagues that I mentioned earlier, they used material that was much older. So this was oak from a house, timber frame house in Avala, which was between 150 and 200 years old. And you can see the batch of timber here on the left. This doesn't seem to be working for me, no. But on the top left here, you can see it's a larger section size rather than the roofing members. It's about 150 by 160. And here on the right, we can see what has happened as a result of the sawing of this into boards. We have a large amount of waste material. The evaluation of this material was carried out in the same way that we did for the spruce in Galway. And here we see the results. That dynamic modulus of elasticity on the top is for the recovered oak, and a new batch of oak that was sourced is shown in the lower part. This resource was then used to make 2 separate products. So in the first instance, 3-layer CLT panels were manufactured, again 60 millimeters thick, but 4 designs were considered this time. So in addition to the new and the recovered, and having the recovered timber on the cross layer, they looked at the inverse as well, having recovered timber on the outside and the cross layers of new timber. And if we take a look at then the results of these bending tests, on the top here, what we're looking at is the global modulus of elasticity for the 4 designs. And this mean value, there's no significant difference in the mean value across the 4 designs. However, we see a completely different picture when we look at the lower graph, which shows the bending strength. And what we have for the 2 lower values on the left, they are the ones that have the recovered oak on the tension face or on the outer layers, whereas the 2 on the right-hand side have new timber. So what we're seeing here is a very significant difference in strength. Now, while it is significant, we're still seeing very high strength values. I mean, the recovered timber values there we're looking at about 45 newtons per square millimeter, which is obviously quite significant. For the glulam beams, 5-layer beams were manufactured, again with 20 millimeter lamina, and they were 100 by 100. And 2 types were considered. all manufactured from new, all manufactured from recovered timber. And here, if we look at the top and we look at the modulus of elasticity, again, we've got matched samples. So yes, we're getting matched modulus of elasticity values. And we're seeing the same behavior in the strength, which I suppose isn't surprising since it's the same batch of material. But there's a significant difference here in the strength of the oak, from the old to the new. And I suppose this points to the fact that we really need to look at a lot of recovered material and test it and understand what are the factors that are influencing the long-term performance. So just to finish up then, or coming to the end, really what we've seen here is that cross-laminated timber manufactured from the spruce, recovered spruce from that roof structure, performed equally well to that of new timber. But when we started to look at the oak, we found no difference in the stiffness performance, but the strength values for the products from recovered oak were about 50% of that from the new oak. I suppose a practical consideration from the point of view of the feasibility of actually doing this is what is the material yield. And in the first case where we had the roof example, the members recovered from the roof structure were actually quite large relative to the size we wanted for those panels. And so what we got there was that the yield was only 28%. But if we had available to us members of a closer size, we would have had a higher yield. The yield for the oak was much lower at 15%. And so in considering the type of material, I personally would not like to see those beautiful old oak beams cut up. And I think for heritage material like that, they're probably better reused as they are rather than cutting them up. But they're, you know, this is just the material that we had available to us in the project, and there should be other applications available. So I see my colleagues here have stop signs coming at me left, right, and centre here. So I will conclude with that. But just to very briefly mention that as part of this work, we have done some other testing, including bond line testing of glue lines, embedment testing of recovered spruce and oak. So I was very interested to hear about the connection study earlier. We also used recovered timber to manufacture ISO timber panels, and an LCA study has been carried out on the use of this recovered material that you'll hear about in a little while. So with that, I'll finish up and I'll hand over to my colleague Ylva Sandin from RISE.
Thanks, Annette. Thank you.
Any book thrown at
So, we've seen that there is a lot of wood in existing buildings, and there are some challenges to the reuse of them, and some questions on the quality of the wood that we can retrieve. So, we have also worked in this project with the question of designing out waste, so thinking of reuse already in the design phase, and finding methods and design solutions for that. So I'm Ylva Sandin, I work at RISE, and I have been a work package leader, but more than 20 people have contributed to this work, both from academia and from industry. And I have 3 persons here representing industry today, and we will discuss experience from this project. But first, let me give you an overview of what we did. Our objectives were first to find a method to optimize a primary design for deconstruction and reuse, which showed to be really difficult. We also wanted to find or suggest new design solutions adapted for deconstruction and reuse, and to suggest how you could structure guidelines for deconstruction and reuse, also called deconstruction plans. So to meet the first objective, we thought that we could create a tool to assess the reusability of a building. And we created such a tool, an indicator system, and it generates a rebuilding index. So it's a figure telling how reusable, how deconstructible and reusable this building is. And this tool exists in an early version. It will need further validation and development. We also found that all stakeholders were not so happy with this method. An architect would not want to design a building, assess it and redesign it. That's not how it works. So it would be better to have some support during the design process. So a design decision matrix was developed by St. Walsh. And also we needed a third method actually, a method to adapt an existing design, a method that was pragmatic and easy to use because we knew we wanted to carry out case studies. And that was in order to meet our two other objectives, the new design solutions and the deconstruction plans. So we found a method to carry out case studies, and we applied it in 5 case studies in 4 different countries. And these, as you can see, are rather small residential buildings, but they represent types when it comes to some are catalog buildings and some are bespoke buildings. Some are massive timber and some are light timber. And through these case studies, we developed or suggested some new design solutions, and we also showed examples of how guidelines for deconstruction and reuse could be formulated. And the persons sitting here were with us through all this work, but we are especially now going to focus on the case studies. So we have with us representing the Everett Grant study. Was it called that? Yes. Nicola Jackson from Robertson Timber Engineering and Offsite Solutions Scotland. Also Janina Östling from Isotimber, who worked with the Villa Forsällasund study. And St. Walsh, who work at University College Dublin and also older architects, and led the study on the Signum Reflect 140 house. So let's discuss experience from these case studies. First, I would like to talk a bit about the situation today, as kind of a background picture. To what extent is deconstruction and reuse considered in the design phase today? And maybe if you could start, St. As an architect representing the architects, or yourself, whatever.
Well, I don't know if I'll represent all architects, but I think from design for deconstruction, I suppose it's only one part of the process that we looked at, but consideration of design for deconstruction and reuse is really, I would say, there's very limited consideration in the general architecture community, to date at least. And I know that there are exceptions. I know that, for instance, many practices in Scandinavia, a number of them are making very interesting and progressive work in it, as well as in Belgium and the Netherlands. But in Ireland, at least, in the general architecture community, there's very little uptake of that process.
And what's the picture? And if I ask Nicola from a manufacturer's point of view, if we consider these catalog buildings, are they designed to some extent today for deconstruction and reuse?
So not at present, but through carrying out this project, some of my colleagues have started to ask questions about how we might reuse these materials in future. So that's had a positive impact. And since this project started, actually, we delivered a house for COP26 in Glasgow, and that was deconstructed, and it's now in its parts, and we're looking at rebuilding that.
Do you want to compliment, Elena?
Yeah, I don't think it's considered very much at the moment, no.
So that leads us to the next question. If this doesn't happen today, what would be good or the best incentives to make it happen, do you think?
Yeah, by regulation could be one part, or if you have an economic incentive, for example, green loans, if you can demonstrate that it is can be reused, the building, or yeah, something like that.
Yeah, the best incentives for it would be to have whole life carbon targets set. I think there needs to be values for that, and make it mandatory to have deconstruction plans in place. I hope that's the case going forwards.
I suppose I don't know if it falls into the category of incentive, but I think that if those, I guess, suggestions that Nicola and Janina have made are coming from the regulatory governmental side, potentially we need to make it as easy as possible for designers to implement those tactics and strategies that will come with more guidelines or greater support in that regard.
Yeah. So you would then perhaps think that an indicator system could be an help if we could carry on and complete it. Yeah, so over to more detailed experience from your case studies, if maybe Janina, you would like to start. The Villa Forsällasund, it's a bespoke building, so it's not a catalogue building. It's built up from CLT and the iso timber panels that are composed of only wood, no insulation or vapor barrier within.
Yeah, it's
and
both load-bearing and insulating, yes.
Yeah. So we analyzed this building, how would it work to deconstruct and reuse it today, and then you figured out if you need to improve it, and then you did some improvements. So what do you want to mention for this?
What we found useful with this case study method, I thought in the beginning it was a bit crude, it was not very specific, but then again it was very useful. It made us go through every step, how to analyzing how to deconstruct the building, and you can find where the difficult parts are, and we thought that was very useful. And then we found that the existing building was, the load-bearing structure could be reused to 96.5% of the wood, and by doing some improvement, then we could reuse 100%. So we found it very useful to do this study. Yeah. And also we developed, it triggered us to develop a deconstruction guide, also very useful, I think.
Yeah, please go ahead, Nicola.
Yes, so for us, it's actually work that Marlene had done to analyse our standardised house type. So although the house type is standardised, the components aren't. And in the house, there were 76 different panels, and there's even variation between the different floors. So now we're looking to standardise those parts or have more common parts. And what it will mean is that we can order in materials at fixed lengths, so there'll be less waste. And it will also make efficiencies in terms of production because we're producing the same part again and again. So it was really useful for us.
So there are economical advantages to this that you discovered through this analysis.
Yeah, absolutely. Yeah.
I think that's interesting. We discovered somewhat had a process like that with the Villa Anneberg, where there were advantages not just connected to circulating, but we found them through this process. And Sinjin, what about your study? What were the most important experience to take away from this?
Well, we looked at it from a holistic standpoint also. We looked at it from assembly through to, realization, and then it's disassembly. And it's something that maybe architects don't really do. So that's, we looked at the scale of the rooms to make the design, utilize standard components, in a higher proportion. And by doing that, the aim was to increase the quality of reuse at the end of the project, not just the quantity of reuse. because there is a I guess a difference between those. There's no point in having extracting materials from a building which can't be reused in the future. So it's just, I think that was quite an I guess an important realization of the case study.
Is there anything else you want to mention, not maybe from your case studies, but from this project as a whole?
No, yeah, I think it just confirmed our starting point that you need to think of the construction already in the design phase, how important it is.
So, what do you want us researchers to do now? Are there questions for us to take further? What are important topics to examine now for us in academia?
Yeah, so I think having a full digital model of the building, a digital twin, so you know what all the components are and how you would use them in the future. And if that could be tested in future research, that would be really valuable for us.
Yeah, and I would like to see actually it was interesting to see the other projects today, because I would like to see this method or standards to be developed because our analysis in this case study was theoretical, so I would like to have some more proven, or so you could trust the results. And the tall timber buildings project and also these hardwood fasteners was very interesting to listen to. So I think we should continue as well but combine the projects.
Yeah, I sort of echo that in the sense that to convince clients and out when you're building, time and cost are everything. So you need to be able to convince a client and a contractor that what you're proposing is feasible, that it's not. We're all wary of cost now. So it would be good to get objective results about how the impact of design for disassembly and reuse strategies have on taking a building apart or reusing materials such as that. So that would be very useful. And then I guess allied to that, material specific guidelines would be really helpful.
Very good topics. We didn't have the opportunity to take us apart buildings and re-erect them, unfortunately. We asked Derome, but they wouldn't let us. And so for the last question, now that the project is over, will you take this question of design for deconstruction further in your daily practice yourselves?
Well, I think the research project has changed the way that I think about architecture implicitly, which is sort of, at the outset, I really didn't expect that. So I think that absolutely it will, I think I'd like to bring it into everyday practice as much as I can and continue to research in that vein.
Yeah, I'd like to see us using deconstruction plans going forwards. I'd like that to be in our future homes that we deliver.
Yeah, and I think that isotimber is already that, so to speak, prepared for being deconstructed. We could use as a unique selling point, actually. But also we focused on this area, so we're already in another project now, Framtidens Design, Future Design. So we're looking into both flexibility and deconstruction. So we're already in a new project for this.
I think this is great positive news, and we will close this discussion with that. So thank you very much.
Thank you.
And I will continue now with showing some examples of new design solutions suggested, and we'll take the Villa Anneberg case as an example. So Villa Anneberg is a residential house in 2 stories, and Derome delivers it. It's built in a factory with large 2-dimensional elements, and they are transported to the building site, and the building is erected in about 1 day, and then completed, of course, in a couple of weeks. And we can see the wall elements here, and floor cassettes to the right. And as you can see, the wall elements are today not completely finished in the factory, but there is an open part of it here with a vapor barrier folded back. So, the case study method. We analyzed the building as it is today, together with Deromes, experienced persons as the research manager, technical manager, structural engineer, and others. And we were researchers, and we sat down and thought about how will this be deconstructed and reused, what will be the challenges and problems, and how could we solve some of them. And in order to do that, we needed to focus on a scenario. So, due to limits of time and resources, we chose only one scenario. So we studied the scenario that after 50 years, this building will be deconstructed into its original elements. These elements will be kept intact and transported to a new place, where the building will be reassembled to a similar or identical building in the same region, so that we will have the same snow and wind loads. And we consider no changes in building regulations. And this could be a good scenario if the alternative is to demolish the building. And other case studies focused on other scenarios. So we have scenarios considering taking apart the whole thing into its components. We found that it would be good to improve 3 details: the wall-to-wall meeting, the wall-to-floor meeting, and the meeting between floor cassettes. And we'll now see some animations of the current details and the improved ones. So first, the wall-to-floor and wall-to-wall meeting. Today, you can see the screws coming there. We have a wall-to-floor meeting, and the wall is screwed to the base plate. Here comes part of a wall element with this vapor barrier folded back and a piece open so that it can be screwed to the adjacent element. Then on site, the vapor barrier is folded back. The joint is sealed with something called a butyl band. And this gap is filled with insulation, a stud, and OSB. And finally, the floor is completed, and the walls are covered with gypsum plasterboard. So disadvantages of these meetings are that in order to reach the screws, you will have to tear away the gypsum plasterboards, and you will have to cut this butyl band, or you will destroy the vapor barrier. It will not be airtight in a new position. So we'll have to rebuild these elements in the factory before reuse. And also there's the question of butyl band. Derome wants to get rid of it as it's not very environmentally friendly. So with the new design, the element comes with the gypsum plasterboard on, and it's more completed. There is now a gap between the wall and floor here. So now it's been screwed, the wall screwed to the base plate, and here comes the second element, and in a more finished state, as you can see, with the gypsum plasterboard on. And it's still possible to screw them together. It's sealed with an ordinary tape, and then this is made good on site. So we got rid of the butyl band. This is completed with the floor, and to hide the gap, we need a skirting board. We also improved the floor cassette meetings, because today there is glue in this connection. Sorry. But with the improved design, there's no glue between the floor cassettes. It's just screwed together, and it can easily be deconstructed. Yeah. So I'll have to stop because I run out of time, but I will jump to this picture. So did we design out waste? Yes, we did to some extent. Because with the current design, all the roof boardings and battens go to waste if we deconstruct and try to reuse it. 20 to 25% of each floor cassette will go to waste, some of the wall studs and all the sill plates. But with the that means that we can reuse 82.7% of the wood or wood-based material in the building with the current design. But with the modified design, only roof boarding and battens will go to waste, the sill plates and nothing else, so that we could reuse 86.4% of the wood or wood-based materials. We also want to know that this new solution is good for the environment, so we want to compare the LCA and LCC for the current design and modified design, and that is what Rafaela has done. So now over to Rafaela. Thank you.
Thank you, Eva, for the short introduction. I would just switch to my slides. My name is Rafaela Ivanica, and I'm from the Technical University of Munich. And I want to give you a brief introduction into the life cycle assessment and the environmental assessment of design for deconstruction in timber construction. First, the motivation. The construction sector right now is responsible for almost 40% of the global CO2 equivalent emissions, and 11% of those emissions are related to the raw material supply. In addition, 850 million tons of the European waste is related to the construction and demolition sector. Furthermore, in Germany, the approved buildings is continuously increasing, as well as the share of timber buildings is in Germany right now with approximately 20%. Therefore, the amount of wood only for the construction sector is growing and growing. Therefore, we have to think about new methods and approaches, how we can meet the growing demand from the construction sector and the other sectors. Oh, sorry, they have the automatic for and also meet the growing demand with the limited resources of timber. That's the reason why we are thinking about the circular economy and the design for deconstruction, and also the recovering timber for CLT might be a solution to do so. And to see if the CLT and the construction circular economy is also suitable from or good from an environmental perspective, we will do this work. So now I will come to my objectives. As Annette and Ilva explained earlier, I will show you the environmental performance of the CLT made from recovered timber and compare them with the virgin timber. And also I will show you the ordinary Villa Anneberg and also compare them with the design for deconstruction and reuse system. To give or reach those objectives, I use the methodology of life cycle assessment, which is commonly used for the construction sector. So let's start with the CLT from recovered timber. Here you can see the system boundary, and to produce 1 square meter of CLT made from recovered timber, we approximately need 0.49 cubic meter of recovered timber. So it's even the double amount of the virgin material is needed from the recovered, because we have a lot of pollution, we have screws, we have lower cross sections, but this also relates to a high amount of residues which can be transferred into energy production. And if we produce 1 square meter of CLT, we also gain the amount of 342 megajoules of electricity and 1026 megajoule of heat. This is the functional unit, so the CLT and the energy, which is the basis of the comparison of the two systems. So in contrast, we have the reference system and also the production of 1 square meter of CLT. But if we take the residues from the manufacturing and produce energy, we are not gaining that much energy as we would from the recovered timber. Therefore, we need a system expansion to have an equivalent amount of CLT and energy. The system expansion can be made option A, from grid, so we use the ordinary energy grid from Germany, or B, from virgin wood. I would like to show you some results now. I only picked the environmental impact categories, global warming potential and fine particulate matter formation. We do have a lot of more, but this would be too much for this presentation right now. So the first bar you can see is the emissions related to the recovered wood. The second bar is the virgin wood with the system expansion from grid. And the third bar is the virgin timber with the system expansion from wood. Here you can see that the green bars are higher, or the emissions with the green bars are higher because we have a higher drying effort. If we use virgin wood, we have a moisture content of approximately 70% and have to reduce them. And another big bar we can see is the light blue one, for example, by the fine particulate matter formation. Those are the emissions related to the incineration. As explained earlier, with the recovered wood, we have a higher amount of residues, which will be incinerated afterwards. And the incineration causes a lot of emissions, in particular fine particulate matter. But the main influence we can see on the system expansion. And the system expansion is also mainly the energy production from incineration wood, which is the third bar, and also the energy grid, which is mainly from fossil fuels and abiotic materials. So we can see that the recovered wood, or the CLT made from recovered wood, has less environmental impacts compared to the ordinary. Let's come to the second system case study I will show you. It's the Villa Anneberg. And here I will start with the reference system, so the ordinary Villa Anneberg, and we put the focus on the ground floor, so on the exterior walls and the floor cassettes from the exterior wall. And the functional unit of this system is 1 square meter of net floor area, and over the lifetime of 100 years, because we have 2 buildings life cycle, as Ilve explained earlier. Here you can see we started the modeling according to the standard 15804, so we're including all building life cycle stages, starting from the raw material supply, the manufacturing, the transportation on site, the assembling, the use stage, and the end of life, as well as the waste management. The use phase of the building are excluded from the study because we are assuming that they are identical for both systems, so they are negligible. For the reference system, we have mainly the end-of-life scenario that the wood is going into the incineration. Only a small amount of the waste is going into landfill or is recycled like the steel scrap. With the incineration, we are producing a lot of energy which is not used in our product system. Therefore, we are transfer them outside of our system boundary, and we can recalculate them to avoid energy from fossil fuel production. In contrast, we have the DFDR system with a different end-of-life scenario. Here we don't have the incineration. Here we are trying to recirculate the wall and the ceiling elements and use them as a base for the second life cycle. When I'm adding the second life cycle of the reference system, it's identical to the first one. If we have the second life cycle for the DFDR system, we use the recovered elements from the first and transfer them back, have the second building, and then the end of life is also incineration. Then the results of this investigation, you can see the reference scenario as the first bar, and the second bar is the DFDR scenario. And just as an explanation, the yellow diamond is the difference between the positive and the negative emissions, because due to the information module D, we have never negative emissions, because we are avoiding energy production from, for example, fossil fuels. Here you can also see that the DFDR system has a lower impact. This is related to the smaller material input, because we are reducing one whole part of raw material supply, which is the main impact of the stage A3, the manufacturing. Here you can also see the small orange bar. This is the remanufacturing of the DFDR systems. They have a really small influence on the impacts. So let's come to the conclusions. Overall, I can show you we have a reduction of the environmental impacts by using or producing CLT from recovered timber and also using the DFDR systems. For the CLT system, I could show you that the incineration of the wood and also the energy production from grid or from fossil fuels have a very high impact on the environmental impact. For the DFDR system, it was able to see that the material reduction, so if you reduce the raw material supply, this also has a huge influence on the environmental impacts. Therefore, when we are implementing the circular economy into the construction sector, we are able to reduce the environmental impacts and also reduce the raw material supply, which we want to have, because we are, only have a certain amount. Despite the positive effects of the LCA calculation, we did further research, which I'm not able to show today. We also made a life cycle costing analysis, and we also developed a life cycle inventory database for the building demolition stage. So we are able to introduce the end of life stage, the demolition stage into the early LCA calculation. And we also give some recommendations about building documentation, otherwise we are not able to recover or reuse materials. Now I want to hand over to my colleague Daniel. He will guide us to the question sector. Thank you very much.
Hello everyone, I'm Dan Ridley-Ellis. You may remember me from the video. I would like all my colleagues to join me on the stage, please. And we have about 10 minutes for questions. I've been monitoring the stream and the Menti, and there are only one genuine question that came in. The other was from me, I confess about that. So the genuine question was for me, so I'll answer that quickly while my colleagues get ready. And that was a question about whether I think that this new grading process will be useful as well for new wood. Actually, that was the genesis of the idea. I was thinking about how we might deal with trying to increase the range of species that we get into the construction market. So dealing with minor species and timber from undermanaged forests, or any kind of situation where we don't have that much information about the original population. So that was what I was thinking, and I was expecting that some of the issues with the recovered wood might also help with that problem as well. Okay, I guess I will invite questions from the audience. Do we have any questions from the audience? Yes, I see a few. Is there someone with a microphone to go around?
Well, thank you. My name is Hans Blas from Karlsruhe. I have a question. When you disassemble a building or walls, you have to, let's say, get out the screws again, right? Have you any idea whether this is possible after a certain time, after maybe loading of the screws or moisture content changes in the timber?
I can only say we discussed that a lot. And I also wonder that very much. Is it really possible to undo it? But
it's
we
difficult.
had, in these discussions with the industry, they judged it's possible. And we also had a webinar with an American expert in deconstruction, and he would just cut through with a saw. So anyhow, for our purposes, we thought this can be deconstructed. But I don't know if you would actually draw screws out. But maybe Janina, you want to comment on that? Yeah, where's the second microphone? What did you?
Yes, no, that's what I was ending our interview here. That it's actually need to be verified to be really reliable. But it's what we do in the production is to undo them, fasten the screws sometimes, and there's no problem. And it's a lot of places where you can change the screws if you want to replace them.
A question at the back.
Hi, Ed Suddy from BRE. Hello, InFutUReWood. Great to see the whole team on stage. Clearly, this is not just a wood issue. So buildings as material banks, the whole principle around circular building assessment and the business cases for delivering it, which is what the part of the motivation is really, really important. And we're seeing it, again, coming back to that financial and investment sector. And I would certainly encourage you to continue your work around life cycle costing, because the key thing there is around carbon risk. So when somebody buys an asset, they're taking on carbon risk on what it's made of and whether it has any future circularity potential, as well as the operational stuff. So it's really, really important to connect in that. So I would just encourage you to continue around life cycle.
I have been in conversation with the Röhm about the prices, and right now the price for the ordinary Villa Anneberg and the DFDR system, they are identical. And afterwards, in 50 years, you may have a value out of the DFDR system. So if you are not doing just the first calculation, it is a value in it. So you will be earning at least a little bit.
Question?
Yeah, this is Frank Brüchert speaking from FEA in Freiburg. I was just wondering about really the recycled CLT, because I thought that is a very high level product for recovered wood. So did you also consider, say, other uses, so not as high constructive, but maybe insulation or things like that?
Well, I suppose in the case studies that were shown, the idea, I think, is that there is a cascading of reuse. So, for instance, the panels that might be taken from the Villa Anneberg may be reused once, and that for the next reuse, if regulations change, for instance, it would be decomposed into its elements, so studs, insulation, panels, and those individual elements would then be reused again, and they would have, if notionally, a very high quality, be high quality reuse items, because they will be sized to standard sizes. And we've looked at the use of, for instance, wood nails instead of screws, which would allow you to just cut them out and have a monolithic stud, and that could be then reused again. So it's really looking to increase the quality of the reuse by, in that way. So hopefully that answers your question, potentially.
But you mentioned wood fiber insulation. Mm-hmm. We were thinking maybe, because you've seen how much reprocessing waste there is with recovered wood, much higher than there is with new wood, and we thought maybe a CLT manufacturer could have a co-product, which would be wood fiber insulation as part of their process. So it would be nice to have some more research money to look into that part of the thing.
We'd be happy to.
Any more questions from the audience?
And I could just add there that we are looking into this also. We have a new application, and we are looking into reused wood, or that you can have not virgin wood or low quality wood, or even like symbiosis cut-offs from the saw industry, to look into our panels. So there might be an option as well.
Any more questions? Yes.
Yeah, Rune Zittem from RISE. You take a responsibility when you're building a house, and have you discussed about who is willing to take the responsibility for the materials where you don't have the history that might be contaminated for different reasons? How is that to be solved?
I think you should.
Yeah, I can say a bit about that. Maybe my colleagues then will pitch in. I think you have to have some kind of sorting or inspection step, as well as the grading, because as well as taking responsibility for the declaration performance, as you say, you have to take responsibility for there being no contamination and other issues as well. So there has to be a very important inspection step.
And maybe in addition, we need some building documentation. So if you know this is wood without preservative and all without coating or something else, you know there is now a hazardous material, so you are able to reuse it. And if you have the stamp, or at least you know it was graded C24 before, so you know what it might be afterwards.
Yes, and I think this is an important issue, is the whole, you know, if we're looking at circularity, we need to have a history of use. So we need to have material passports that will track any changes that have been made. And certainly if there are, you know, coatings or whatever, that we're aware of those. And then when we get to the next use of this material, you know, we can remove coatings that are there by simply reducing the section. But the whole thing would hinge on having material passports and a history of all of the materials in our buildings, which is really important, not just for timber, but for all of our buildings.
So this leads into my fake question that I asked on Menti. Thinking about the Click Design project, because we've mentioned fasteners. Fasteners are a big issue, but preservative treatment is another issue. And in some countries, including my own, we have an attitude of default treatment. And that's partly because we don't have the confidence in the construction quality and the detailing to rely on the detailing and the natural durability and the maintenance and approach to do that. And I was just wondering whether the work of Click Design, improving confidence in detailing natural durability and so on, will help us move away from the default attitude of treatment, which will then improve the circularity of timber.
You want one of us to answer that?
Yeah, or at least say yes. For the people online that are listening.
Yes. I have to say I was very taken with Click Design, wherever you are in this room. There you are, up in the corner. I teach technology at University College Dublin, and I want to use those tools with my students because I think it will make them understand all the issues involved in choosing timber, how to choose timber and how to design it, and undoubtedly would have an impact on the architectural profession as well. So I think that's a huge step forward to have a tool like that, actually.
Thanks. Well, this is great because the theme of our project was circularity. Circularity of the material, but we were also thinking about circularity of the knowledge link. We were looking at demolition and the issues that building design and construction was creating at demolition so that it would then inform the design and construction of new buildings. So it's fitting and poetic that we end with a loop back to the first project that we talked about today.
Intentionally.
All purposeful and by design. But I would like to have Karen back on stage. She's already here.
Yep.
To close the project. We will stay on here.
It's 10 past, but for us it's okay. Yeah, okay, we can have one more question.
May I? Thank you. It's more a remark about the last issues. I think you did research about reuse and recycling of timber structures. And we have a number of those projects in concrete, in steel, in plastics, in other construction as well. What you are talking about in your last discussion is a problem we have to solve, in my opinion, European-wide or on basis of the state. We need systems how to demonstrate what is in our buildings. A BIM data is it really available on private basis after 50 or 70 years? Who will keep all this data safe? So the total system of reuse and recycling must be on another level than it is discussed on the levels which are dealing with certain constructions. And I mentioned that also to my own government 2 days ago. We need a common research how we are able to handle these issues. Also storage in between, for example. Also that according to European right, first of all, you have waste. And then you have to come back from the waste laws to the construction product laws. And this is also a difficult step, especially in my country probably, but I think it's also in other countries. You have, every time you want to get rid of anything, that's immediately waste. And then you are in the legacy of waste. And then you have to come back. And there are a number of really general questions we have to solve. And this is, in my opinion, not solved on material basis. This must be solved on a general basis. Thank you.
I mean, this is something we've actually discussed at length within the project, this whole issue of the lifespan of a building being 50 years, and what are we talking about happening in 50 years, and who's going to resource the updating of a database if we have, it's all very well the manufacturer providing you with information on your CLT panel or timber frame wall. And then once it's constructed, you can have your as-built drawings and you know what happened. But after that happens, in the maintenance phase and the use phase of the building, this is where the difficulty is. And then what kind of technology are we talking about? But I mean, if you look at where we are today, I think BIM is really the only game in town. So I think the industry across all sectors of the construction are increasingly adopting BIM as the norm. So I think that is probably the way that we're going to have to go in the future with this, and embedding material passport information within BIM models or the next generation of BIM models. But that doesn't solve the problem about who's going to keep these models updated over time. And that's something that I think you're totally correct.
I think
to be addressed.
Hating to disagree with you, Annette, I wouldn't actually agree that BIM models are the way forward, or at least not the full way forward. I think, for instance, computer software is changing so quickly. One group of architects working in an office cannot use the same model as another group because they're using different years of BIM. So imagine that in 50 years' time. It's just, you know, the idea of it is actually impossible to fathom, that they would retain the software and then have it ready to go. And also you're relying on an architect or a technician or somebody like that having the ability to update it as it goes along. And while I think that I can understand the simplicity and the sort of the idea of having this holistic model, in reality, from experience, work is done on a piecemeal basis, sometimes very small, sometimes more significant, and by different people and at different times. So trying to update it, I think, will be just on, you know, on an industry-wide scale will be just almost impossible. We've discussed it as well, and I mean, the ideal situation is that you would have the information of the building chiseled into the pad stones of it there and just have it there at hand. So it sort of needs to be made as accessible as possible so that they can't disappear. I've had instances where you'd look for documentation and it would have, you know, been thrown out. You know,
yeah, the amount of information you're going to need, you're not going to chisel into.
Oh no, I'm
so you're looking at some sort of electronic storage of this information, and I agree. The BIM way forward is not without significant challenges, but it's what we have today, and hopefully other technologies will develop into the future. But
what about artificial intelligence? It can also automatically maybe update old fights or something like this. So it's all, yeah, of course, we have to discuss
I think I'm nominally in charge of the section, and I should say, this sounds like a conversation that we should all be having outside.
Yeah. For dinner, maybe.
Yeah.
So, very interesting, but we have to close this. And I think this final discussion, in a big way, showed this complexity in this project. And when we started this, we was one of the first projects working with these wood building structures. So we have dealt with a lot of discussions and problems that we have tried to solve. And as you remember, now we conclude this, and this main findings is they are difficult to deconstruct or disassemble the structures that are built today. And that's why they are more or less almost demolished. And as we saw, then the quality became rather poor. But we have at least some positive, promising results from this project. And we can see that design for deconstruction and reuse can be implemented with small changes and existing technologies. So we don't need to invent everything one more time. And the design for deconstruction and reuse can contribute to reduce the environmental impact of timber frame construction for residential buildings. And we also can see that products from recovered timber tested structurally show similar properties to equivalent new products. And from the test, we can also see that the environmental benefits can be achieved from the use of recovered solid timber in high-quality CLT panels. And also that recovered spruce and oaks show promising results of stiffness and density compared to new timber. A new framework for strength grading was also developed. And we can also see there is a huge amount of wood in the existing building with potential for reuse in the future. And as we have seen, it's possible to move the house also. But this is the contact information in the 7 countries. And to get in contact with. And we have rather a lot of information on our website. And we have also here the link to our YouTube channel. So you can see more, I think it's 15 videos or something like that, about different subjects that have been performed. And we have, to the right, you can see a report that we are almost finished with, that we compile a lot of the results. That's the light version of the reports. The other reports are like this thick. So this is the light version for easy reading. And by that, I think we say thank you very much and good evening.